Okay, so well, in the lecture today, we will start a new topic, which is about the introduction of the highway subgrade structures. We want to analyze the properties of the subgrade soils and identify whether this for any type of the subgrade soils is appropriate for the pavement structures, which will be applied on top of the subgrade. And what happens if the soil is not appropriate? How we can process the soil, the nature soil in the field, and how we can try to find out the most appropriate way to make sure that the nature soil can satisfy the minimum requirement of the pavement structure. So this is actually a very important step for us to place the pavement structures on top of the field. So for this study, we will first have a review about the layer system for the pavement design. As we introduced in the first several lectures, there will be multiple layers that will be applied for the pavement structures, especially for the flexible pavement. Usually we will have the surface layer, base layer, subbase layer, and these three layers are actually called the structure of the pavement structure. And the subgrade layer will usually be the soil, the natural soil in the field. And we, at most of the time, we will to apply some compaction to that to the in situ soil, and as we know that the soil in the field would be its natural soil does not have any very large aggregates in the soil. So at most of the time, those kind of soils will be very sensitive to the moisture contents. And if there's some rains or some waters entering the subgrade, it will significantly reduce the strength of the subgrade layer. So it's relatively weak, and we need to determine whether this kind of, even though we know that the soil is weak, but we still need to check whether this kind of soil is appropriate for the pavement layers on top. So in this topic, we're going to introduce the requirements of the subgrade for the pavement design and the potential factors which will affect the subgrade behaviors, and the consideration that we have to put in the design of the subgrade layer. So let's go through them one by one. Basically, there will be a set of the features that we want the subgrade to have in order to provide a reliable subgrade layers for the to support the pavement structure. At first, we want the subgrade layer is strong enough, which means that we want the soil has sufficient bearing capacity, which is usually measured by the California bearing ratio, and with that, the soil can support a very heavy load from the pavement structure. And also, the second feature is like we want this subgrade layer to have the smaller deformation, and this is a very important for us to control the failures of the pavement structure. If the deformability of the subgrade layer is high, means that it's easy to cause the cracks or the changes the shape of the pavement structure, and that will cause the distress of the pavement design and even result in the structural failure of the pavement structure. And the third thing is like we want to make sure that the property of the subgrade that we designed can last for a very long time, and they are consistent for a long time, which means that we want them to have the time independent properties. because this is the fundamental requirement for the design life of the pavement structure. Usually, the pavement structure will last for 20 or even to 50 years. So we anticipate that the property of the subgrade will be consistent in this period. And another thing is about the impact of the environmental conditions. And especially like if we are talking about the pavement in Ontario area, the temperature and the rainfall conditions at different seasons will be very different. And if the subgrade layer is too sensitive to those changes, then it will cause it will have a very negative impact to the pavement structure, and it will easily lead to some distress. Another thing, the last thing is the drainage condition. So we know that there will be some rainfall to the road, and some of the waters will be fall down to the behind the pavement structure. And at the bottom of the pavement structure, there will be the subgrade layer. So the subgrade layer should have the capability to remove the water from the pavement. And in that sense, we can minimize the impact of the water contents to the pavement structure. So those are the 5 basic requirements, or 5 features we want to maintain for the subgrade layer. And this is also the basic requirement for us to develop a reliable pavement structure for one specific road. And among all those features, the moisture contents has the most significant impact to the property of the pavement of the subgrade layer. And usually for the subgrade layer, which the in situ situation, in situ soil will have relatively higher percentage of the fine particles. And for this type of the soil, they will be very sensitive to the water contents, and there will be some issues from the, for example, the waters due to the permeability of the pavement structure. The water will fall to the subgrade layer. There will be some capillary effect of the water from the waterbed behind the ground. And this will all increase the water contents of the subgrade layer. And the increasing water contents will reduce the strength and the stiffness of the pavement layer. And also, if the water contents increase, you will observe the expansion of the wallings for the soil. And this means that with the changing wallings, there will be some very high deformations about the pavement layer, and it will also cause the expansion of the upper pavement structures. And this is actually a very serious issue, especially when the soil applied for the subgrade layer is an expensive soil. We will have some introduction about expensive soil in the rest of this class. As I just explained, the expensive soil can lead to severe distress on the surface of the pavement structure, and also by increasing the water contents, there will be some first HEAVE effect for the first susceptible soil, and this is another issue which is related to the temperature and also the water contents, and sometimes the effect of the moisture on the pavement performance, it would be also very complicated, not only about the cold weather, but also about the hot weather. For example, at the hot weather, when the temperature is very high, there will be some increase about the tensions in the front of the pavement structure, and also due to the increased temperature, the capillary raising effect for the water will be high, and it will increase the water contents in the subgrade layer and the pavement structure, and this will cause some additional issues from the properties of the subgrade layer. Generally, with this figure, you can find out the impact of the water contents to the reductions about the strength and stiffness of the subgrade layers. And in this figure, you can see 3 lines, which each one will represent the relationship between the axial stress and axial strain. Here you can see that by increasing the water contents, for example, from 11% to 15%, the maximum stress that can be supported by the subgrade by this kind of the soil will decrease dramatically. Like if at 11%, the maximum stress could be around 42 or 42 psi. But if you increase the water contents to 15%, the maximum stress will be reduced to around 17 psi, and you can see a very huge axial strain, which means that a very large deformation about the subgrade soil, and this all indicates a very what can induce a very significant distress to the pavement structures. And also we have in the MR test, we do some analysis about the impact of the water contents, and we can find out the reductions of the resilient modulus with respect to the increase of the water contents. And even though there are some materials, some soils will be sensitive to water contents, some of them will be less sensitive, but we can see the general trend, like by increasing the water contents, the resilient modulus will be smaller, and it means that the stiffness of the subgrade soil will be smaller, and it means that the subgrade soil is weaker to support the pavement in the front about the pavement structures above, and this will be easily causing something about some distress, such as the rotting, the longitudinal cracking, and so on. And usually for the materials, for the soils with higher fine particles, the impact of the water contents will be larger. So the percentage of the fine contents is the one critical variable for us to verify whether, or for us to evaluate whether this type of soil is appropriate for the subgrade layer. Another thing that we need to think about with the consideration of the water contents is the loading or the compactive effect. Actually, with a higher compaction, you will find that the soil or the subgrade layer would be stiffer, and with that you can a little bit you can reduce the impact of the water contents a little bit. Here you can see in this figure you can see the result and the different compactive efforts for the different compact pressure. The triangle represents the pressure of 276 psi, and the circle will be 136, and the wide circle will be 65 psi. You can clearly see the stress. Well, this would be stress for 5% reductions in for 5% strain, which will usually represent the threshold for the failure. And here you can see that by increasing the pressure, the stress that it can support would be larger. And similarly, what we will observe, like by increasing the water contents, which would be the x-axis, well, you will still see the decreasing about the maximum stress, the required stress that can supported by the subgrade structure. With that, we can consider that if there's the one way for us to improve the property or to improve the features of the subgrade layer is increase the compactive effort, apply higher load to compact the subgrade soil. But the water contents is still a significant factor. As you see that if the water content is higher than 20%, almost the benefit of using the compaction can be removed due to the high water contents and the significant reductions in the stiffness of the soil. That's the impact of the water contents. The others factor that we have to consider is the expansion of the soil with respect to the water contents, and usually this one is called the expansive or the swelling soil. This type of the soil would be very sensitive to the moisture or water contents, and if the moisture contents increase, the changes about the volume would be very high. Usually with higher water contents, they have larger volumes, and with smaller water moisture contents, the volume will be smaller. So they have the shrinking effect. The magnitude of the volume change it's actually very different based on different type of the soils, and as we just see that the moisture contents will affect the changes of the volume. So we need to identify the shrink swell potential for the soil, and if we find there is some soil which will be the swelling or expansive soil, we need to carefully process that soil to either remove the soil from the subgrade layer, or we need to apply some chemicals to reduce the expansive efforts of this type of the soil. Generally, if the shrink swelling potential is very high, we will observe a lot of distress applied to the pavement surface, such as the longitudinal cracks near the pavement edges, or they can result in the very significant surface roughness, like the road will not be even along the pavement lanes, and this would be very common if you are especially in some place in Saskatchewan, not quite common in Ontario, but in Saskatchewan there will be a lot of expansive soils. Here we have two figures to show the potential distress can be caused by the expansive soil, and from the figure on the left, you can see the uneven surface of the pavement structure, and for the surface for the figure on the right, you will see the very large crackings along the pathway, and those are all caused by the expansive soils applied for the subgrade layer. And so as what we just explained, the expansive soil has a very significant impact to the reliability of the pavement structure. So as the pavement designer, we have to evaluate what's the swelling potential of one soil. Generally, we can call the equation here to calculate the percentage of changes in volume due to the absorption of water. And this one, in this figure, in this equation, S would be the percentage change in volume. And it will be in the function of plastic index PI, and also the percentage of the clay size particles, which would be the portion with the grain size less than 0.002 millimeters. And in this equation, we have two coefficients which will be calibrated from the empirical data, A and B. And also in the equation A, it would be a function of the plasticity index and the percentage of the clay-sized particles. So A equal to Pi divided by C minus 5. And also you have a component with about the value of C. So generally, when Pi is less than 20, we have two values which we have the values of A and B calibrated from the real data. A is 3.2 times 10 to the power minus 5, and B is 2.259. And for all the other categories about the plasticity index, we have it's between 21 and 30. We have a set of the value 31 to 40 and larger than 40. So for the calculation of the swelling potentials, you have to use this equation and measure the plasticity index and the percentage of the clay-sized particles. And so once you know the swelling potential, which is evaluated by the S, the percentage in the previous equation, then you can identify whether this soil is expensive or not. Usually, if the swelling potential is less than 2%, we say that is a non-expensive soil. And this one will usually equivalent to the soil with the plasticity index between 0 and 10. And if the swelling potential is between 2 and 4, it's moderate expensive soil. If it's larger than 4%, then it's a very high, as in a very high expensive soil. And if it's that, you will need to think about remove this type of the soil from the ground. Usually in Canada, the expensive soil will be in Saskatchewan, and the figures in the previous page are all captured from Saskatchewan. So in the summary, the expensive soil can cause the pavement distress in two aspects. First is the swelling. The second one is the shrinkage. So this is it is caused by the changing of the water content. Sometimes by, for example, if there's some rains, the water content will increase, and then it has an expansive effect. And at one sunny days, the water content will reduce. Then you will observe the shrinkage effect. And this kind of expansive and shrinking effect will cause the distress of the pavement structure. And you will usually observe the longitudinal and transverse cracking when the subsurface flow of the moisture travels in one of the two directions and cause the vertical road movement. So this is we will observe the waves at the surface of the pavement. And you will also see the block crackings across in the road, and this will be the is caused by the repeated load of the traffic to the segment with the swelling soil, and you will observe the alligator cracks across the pavement structure. And so this would be two common types of the distress caused by the expensive soil. And the way for us to solve the or to minimize the impact of the expensive soil, the first one is straightforward. You just remove the swelling soil and replace with new soils which are not expensive. So that's the first method, but of course this method is the budget for this one it would be very high because you need to considering getting new materials from different place. And the second method is that you can apply some partial encapsulation or some full encapsulation of the swelling soils. With that, we can control the swelling effect of the soil, and then the impact of the water contents to the swelling soil will be minimized. The last one, which is also commonly applied, is applying some stabilizations, such as lime or cement stabilizations for the subgrade soil. And then we can control the swelling potential of the soil to some range that could be accepted by the pavement design. So all these three methods are applied for the pavement design and pavement projects in modern days. And that's the second one that we want to learn about the subgrade soil, the swelling soil. And the other thing which is related to the soil, the other type of the factor we have to consider is about the combined effect of the water contents and the temperature, which will be applied for the first soil effect in soil. So it usually happens at some region with low temperature, especially low temperature in the winter season. The first action will usually cause differential heaving. Will make the surface of the pavement very rough, and also can potentially cause the crackings, and it will sometimes, if all the waters behind the pavement structure is freezing, then they can block the drainage system of the pavement structure. And the low temperature will also reduce the bearing capacity of the subgrade layer during the soil period. So at that time, they will actually have very high water contents. And depending on the type of the soil, this effect can range from slight to severe. And also the severity is related to the uniformity of the subgrade soil, the climate conditions, and also the availability of the waters. So there will be more instructions about the detailed instructions about what happens, how the frost and soil effect in the Ontario area. So the soil effect on the frozen soil will actually increase the water contents. So the ice behind the ice in the soil will be thawed in the springtime, and it will increase the water contents of the soil, and then reduce the strength and stiffness of the soil. In the winter time, it will probably decline because you have the ice in the soil, and then the ice will be relatively stronger to support the pavement structure. But in the springtime, when the temperature increases, all the ice behind in the soil will melt, and it will make the soil loose, and then the strength and stiffness of the subgrade will reduce dramatically, and that will be the time you will observe the severe damage of the first soil effect to the pavement structure. So these two figures actually show some typical deformations caused by the first soil effect. The figure on the left shows the differential deformation. You can see the waves, which is quite similar to the expansive effect. You will see these waves along the pavement, along the road, and depending on the loadings and the soil effect, you will observe significant alligator crackings along the rail paths, and this will can potentially create the failure, the structural failure of the pavement. And the figure below actually shows how the ice is actually the first effect will be formed in the subgrade layer. Usually, we know that for nature soil, there must exist some of the voids. If the void is large enough, and considering there will be some of the waters in the soil, then the water will collect in the void, and due to the very low temperature, they will become the ice, and it will make the void larger, and in the meanwhile it will attract the water from the surrounding area, and this is one effect. And once the void or the ice length gets larger, it will then attract water from the waterbed behind the pavement structure, and this one is usually caused by the capillary movement of those the waters from the waterbed. And so the capillary effect, the capillary movements of the soil in that kind of soil is a very significant criteria for us to identify how significant the first soil effect of that soil. So with that, we will need to find a way to calculate the capillary raising rate. Usually, and I will show you the equation to do the calculation. But before I go to that, we want to understand what's the mechanism of what's the detailed mechanism of the first heave. So usually the surface tension increases with the decreasing temperatures, and the capillary rates increase at low temperatures. The water will draw from the waterbed behind the subgrade layer, and the freezing temperatures will cause the water in two voids to freeze, and also it will make the volume larger. And based on the capillary effect and attract all the waters from the nearby area, the ice length will increase, and once the temperature reaches to a very low value, then the growth of the ice length will be halted, and then no water will enter to the ice length, and that will create the changes of the volumes or about the subgrade layer, or we have the expansive soil in that area, and it will then, by increasing the volumes of the subgrade, it will then raise the surface of the pavement structure, which will create the waves or first heave along the pavement. So that's the mechanism for the first heave. And as I just mentioned, that the capillary raising effect, capillary movement of the water is very important for the effect of the first heave. So we need to calculate the rate of the capillary raise. The equation here will show how to calculate the capillary raise, which is defined as the capillary raise height. You will identify how high or how depth the water can be attracted to the ice length, and the value is C divided by E times D10. Here, C is the coefficient, and this one should be calibrated from the empirical data. Usually, it varies from 0.1 to 0.5 square centimeters, and the D10 is the particle size at the 10% passing. So it will represent the grain size with the sieve size with 10% passing of all the particles. And E is the void ratio, which is also in the constant. And if this is actually a complicated model to calculate the capillary raise. We can also use a very simple model, which will only determined by the particle size at 10% passing. So that is 0.306 divided by D10 divided by 5. So here this table actually shows the capillary rates in the soil for different type of the soils. Varies from the gravel soil to the silt soil. Actually, it's highly related to the grain size. If the grain size is for the fine gravel, the grain size is between 2 to 5 millimeters. Then the capillary rates is only 2.5 centimeters. But for the finer particles, like for the silt with the grain size of 0.02 to 0.05, then the capillary raising height could be more than 2 meters. And this is a very significant capillary raising effect. And obviously, with this kind of value for the silt, it will be very easy for us to observe the first heave during the winter time. Of course, for the generation or for the formation of the first heave, there will be some required conditions. First of all, we need to have the freezing temperature. The temperature should be low enough to change the water from liquid to solid. And then the soil should be first susceptible. And also we must have some waters behind the in the soil or behind the subgrade layer. And the water table or the water bed must be within the appropriate capillary raise zone. If the water table is the depth of the water table is too high, then you cannot get any water. I mean, for those voids, the iceland, they cannot attract any water from those water table. Usually for a groundwater table, water level is within 1.5 meters of the subgrade elevation. So that's common value that it changes at different areas. And another issue is like for some region with very deep frost penetration, the groundwater at even a greater depth could have the influence to the heave. So this, especially for some, let's take an example in Ontario. For some place in northern Ontario, the frost penetration could be more than 2 meters or even 4 to 5 meters. So in that area, it will be very easy for us to observe the first heave. So to identify the first heave effect, we first need to check whether this soil is first susceptible or not. So with that, we can actually check the permeability and permeability rate and the capillary rate. The permeability represents how easy the water can filtered through the soil. The capillary will represent how high the capillary rates will be. Usually, with higher permeability, the capillarity will be smaller. So the first susceptible soil will only first enter the region in between with moderate permeability and capillarity. So usually for the soils with a large amount of the silt or silty soil or very fine sand, they will be defined as the first susceptible soils. For the heavy clays or for the gravels, it will be less likely to have the first heave. And with that, we also have another criterion to determine whether the soil is acceptable for the subgrade layer. This one is actually defined by the manual by MTO. This is actually one manual for us to design the pavement in Ontario. So the triangle here will shows which material will be acceptable, which one will be in the under the borderline and which one will not be acceptable. This will be colored in, will have 3 different colors, white, red, and gray. So usually for the high silt content and low clay contents, they will not be acceptable for the subgrade. So in this kind of in this table, in this triangle, you can actually check the percentage of the sand, the percentage of clay, and the percentage of silt. Sand represents the grain size between 2 to 0.05 millimeters. Clay will be the grain size less than 0.005 millimeters, and the silt will be the size between 0.05 and 0.005 millimeters. For example, if we have the silt percentage of silt around 20, and we have the clay around the clay around 60, and for the so this would be 20. With the for the clay around 60, and then for the sand there will be another 20. Then you can find out the location of this of your selected material, which would be or the 20 should usually be around here. So this would be the line you have to take from the sand, from the percentage of sand, and this is a line from the clay, and this is a line of the silt, and the interaction would be the point for the material you select, and this one is located in the region with the white color, so it's an acceptable material. If you find anything that falls in the gray area, then you have to skip that, or you have to find a way to solve the first heave effect. So I think I only have 3 minutes left for this lecture. So I will stop here. Do you have any questions so far about the features of the subgrade materials? Okay. If there's no question, there will probably that's probably all about the lecture today, and we will continue the rest 5 pages in the next lecture. Another thing is about the homework 1. We will assign the first the homework 1 will be assigned tonight, and you will need to work on the homework 1. The deadline will be next Friday. So just let me know if you have any difficulty to work on the problems, and feel free to let me know if you have if there's any part that is not quite clear. The problem 1 is about the soil property, and it's very important. It's very helpful for you to understand the CBR test and ML test. Okay. Any questions? If no, then that will probably be all today. And for those who have the lab sessions next week, you just follow the schedule on Avenue to Learn to take the assigned lab. And we have TA and lab technicians there. And I will also visit the lab during the lab sessions, and let us know if you have any questions. Okay, that's